In this video, I want to do one problem in detail, which is very useful to understand basic notions of group theory, because many of the properties that we have so far learned are used in this problem, and if you understand this problem fully, it is very good and it will tell you that you have understood everything that has so far been covered. Okay, so, the problem that I want to discuss in this video is the following. Show that any group G of order less than or equal to 5 is abelian. So, that is the problem. So, I am going to recall some terms here that I covered in earlier videos. What is the order of a group? So, recall that if G is a group and actually if G is a finite group, if G is a finite group, the order of G, which is denoted by this symbol G within bars, is the number of elements in G. Okay, so, order of G is the number of elements in G. So, in the problem, the question is to show that every group which has order less than or equal to 5, meaning any group which has 5 or fewer number of elements is abelian. And what is abelian? G is abelian if A B equals B A for all A comma B in G. So, we say that A and B commute So, the symbol that A B equals B A in words means that A and B commute with each other, which is to say that the order in which we multiply them is irrelevant for the final answer. So, G is abelian if every pair of elements in the group commute with each other, and this is a property that groups have, and not every group is abelian. That also I want to recall before we got to solving this problem. If you recall, the group S3, symmetric group on 3 letters, is the group of bijections of a 3 element set, which we denoted by 1 2 3. And if you recall, in the earlier video where I discussed S3 in detail, we actually listed all the elements of S3 and understood some facts about these elements. We saw that order of G was 6 and S3 was not abelian. Okay, so, if you go back to an earlier video, you will see that we have explicitly showed that there exist 2 elements in S3 such that they do not commute. Okay. So, that S3 is not abelian and it has 6 elements, and the problem asks you to show that any group which is smaller than that, meaning having 5 elements or 4 elements or 3 elements or 2 elements or 1 element, must be abelian. So, the smallest group which is not abelian is of order 6, which is S3. So, now let us go ahead and solve the problem. So, let us solve it. So, the basic idea of the solution is the following. We are going to show essentially that if a group has 5 elements or less, there are just not too many elements, just not enough elements for a pair to not commute with each other. Okay, remember that if a group is not abelian, it must be the case that there exists 2 elements that do not commute with each other. So, maybe I should write this. So, if G is not abelian, because the definition, remember, is that if G is abelian, if so the definition is that G is abelian if you give me any pair of elements A comma B in the group A B equals B A. This must be true for all elements A comma B. So, what is the contrapositive of this? If G is not abelian, there exist 2 elements, let us say A comma B in G, which do not commute with each other. So, such that AB is not equal to BA, and the goal for us in this solution is to show that if a group has 5 or less number of elements, it cannot have just that is not as 5 is too small a number to admit 2 elements which have this property, which do not commute with each other. So, we are going to consider 5 cases. We note that a group is a non-empty set, because a group has to contain the identity element, that is one of the properties of a group. So, group has at least one element. In our problem, we have to show that any group which has less than or equal to 5 elements is abelian. So, we will consider cases. The first case, order of G is 1. If order is 1, that means there is exactly one element in G, and every group must contain the identity element. So, it must be E, and this is certainly abelian. Why? You can see this, it is very easy to see it is abelian, because in order to be not abelian, there must be 2 elements which do not commute with each other, but G has only one element. So, there is no question of having 2 elements which do not commute with each other. So, this is okay, this is very easy. Case 2, order of G is 2. So, let us enumerate these elements. So, as I said earlier, every group contains E. So, that must be the identity is one of the elements. Okay. Now, in this case there is one more element which we will call A. So, that means E and A are the 2 distinct elements of this group. So, note that in particular we have A is different from E, right, because G has 2 elements, one is E, the other we are calling A. So, certainly A is different from E. Now, if G is not abelian, again let me remind you, if G is not abelian, there exist 2 elements which do not commute with each other. If in this case, if G is not abelian, that means E and A do not commute with each other, but that is certainly not the case. I mean, E and A do commute with each other, because every element in a group commutes with identity, right. So, recall that in general any element in a group commutes with the identity element. So, E A is A E, that is part of the definition of a group, that A which are both individually equal to, remember, A. So, G is abelian in this case also, right, because the only 2 elements are there and they commute with each other. So, G is abelian. So, in this case G is an abelian group. So, we are done with order 1, order 2. We have to still consider order 3, 4, 5. So, case 3, order is 3. By the same convention as in the previous case, I am going to enumerate and give names to the elements. E is one element, that is the identity element. Let us pick A as the second element and let us pick B as the third element. So, as before, we have E, A, B are distinct elements. In other words, A is different from E, B is different from E, and A is different from B. These are G has 3 different elements and I am calling them E, A, B. E is the identity element, A and B are non-identity elements. Okay, now again, if G is not abelian, it means that there exist 2 elements which do not commute with each other. So, only possibility in this case must be A and B, because A and E commute and B and E commute. The question is, do A and B commute? Do A and B commute? So, let us do the following. So, let us look at what can be A B. So, what can be A B? By which I mean, remember G is a group and I have given already names to its 3 elements. G is a group of order 3 and I have already given names to its 3 elements. I have called the identity by E, the other 2 elements by A and B. But G is a group and A and B are 2 elements. So, A B must be in the group. AB is an element in the group, right, because we have a binary operation on the group. A and B are there, and when you perform the binary operation on A and B, the output is again in G. So, AB is an element in the group, which is just E comma A comma B. So, we have three possibilities: AB must be E, AB must be A, AB must be B. So, either this or this or this, right. AB is an element of the group which has three elements listed as E comma A comma B. So, it is either E or A or B. So, can it be A? Now, I am going to invoke a very important property that we have in a group that we discussed in an earlier video, namely cancellation property. So, if AB equal to A, multiply both sides by A inverse. So, we have A inverse AB, A inverse A. Note that A inverse is also one of the three elements, but I do not need to actually consider which it is. It is A, E, A or B, I do not care what it is. It is an element in the group. So, I can multiply by that, right, which is going to give me, by associativity I can do A inverse A, which cancels and I get B equals E, right. So, in the cancellation property directly gives this, right, because if AB equals A is nothing but A times E, then I cancel A. I have just spelled it out, but this is what we have. But is B equal to E? Certainly B is not equal to E, because they are distinct elements. So, this is not possible. So, this is not possible, I will say that. So, AB cannot be A. Similarly, AB cannot be B, because the cancellation property says B is equal to BE, I cancel B and I get A equals E, right, but A can't be equal to this can't happen, this is not the case, because the three distinct elements are called E and A and B. So, A can't be same as E, otherwise we would not have given it a new name. So, this can't happen. So, AB must be E, but if AB is equal to B, AB equals to E rather, AB is equal to E. So, this means that B is A inverse. Remember that if AB equals E, B is A inverse and automatically BA must be E. So, A and B commute. So, the point here is that the important point, just like I said earlier that every element commutes with the identity, an element and its inverse always commute with each other. That is the point. So, in this case A and B are inverses of each other and they commute. So, AB equal to BA. If AB equal to BA, then G must be abelian, right, because if G, remember, if G is not abelian, there must exist two elements in it which do not commute with each other. In our case, G is a group of three elements, E commutes with A, E commutes with B. Only possible violation of abelianness is if A and B do not commute with each other, but we have just concluded that A and B commute with each other. So, G is abelian. So, we are done with case 3. So, now case 4. So, that means order is 4. So, let me now do the following. So, I am going to write G as okay. So, G has 4 elements, right. Let us call them A, B, C. The non-identity elements are A, B, C. But now I will do the following. Suppose G is not actually, let me take that back. So, I do not want to enumerate these elements at this point. So, suppose G is not abelian. right. Suppose G is not abelian, then by the point that I mentioned at the beginning of the proof or beginning of the solution, there exist A comma B in G such that A B is not equal to B A. This is the definition of group G not being abelian. But now what are the, but G has only 4 elements, that is what we are going to invoke. What would be the elements of G? E is an element of G and A, B are second and third elements are of G, must be. E, A, B must be 3 distinct elements of G. Why are they distinct? See, because A and B do not commute with each other, neither of A and B can be E, because if A is E, B and E will commute. Similarly, if B is E, A and B will commute. Because every element commutes with E and A, B do not commute with each other, they are different from E. Not only that, A and B are also distinct, right, because if A and B are equal, not A must be different from B. Why is that? Because if A equals B, then what is AB? Then AB is just A squared, but that is also same as BA. So, A and B commute, right, but I am assuming that A and B do not commute. So, A and B must be different. So, EAB must be 3 distinct elements of G, but G has only 4 elements. So, there is room for only one more element and I claim that that must be AB. So, now what must be AB? By the previous case we have said that AB, so what can be AB? AB has to be E. Can it be E? Let us explore that. Can it be A? Can it be B? Okay. So, can AB be E? If AB is E, A and B are inverses of each other. Right. If AB is E, they are inverses of each other and hence though they commute, but that is clearly wrong because I am assuming that they do not commute. So, AB can't be E. AB can't be A because of the same cancellation property that we discussed in the previous case. B is must be E, but B is not equal to E. So, that can't happen. Similarly, in this case A must be E, which can't happen. So, AB, so the conclusion is, so we conclude AB must be the 4th element of G. So, G must be A, E, A, B, A, B, right, because we already have 3 elements E, A, B and A, B can't be any of them. A, B can't be E, A, B can't be A, B can't be B. So, A, B must be the 4th element. Okay. But now what has to be B, A? But what is B, A? B, A is also in the group, right. So, B, A can be E, but if B, A is E, the same problem happens. B and A are inverses of each other and hence they commute, which is not possible. So, B, A can't be E, B, A can't be A for the same reason as before and B, A can't be B. So, B, A must be A, B, right. So, again contradicting the hypothesis. So, we cannot have, in other words, so is it clear? So, B, A must be one of the 4 elements because there is no more room in the group. Group has only 4 elements and we have already identified 4 distinct elements, but B, A cannot be E because in that case they are inverses of each other and they commute. B, A can't be A, B, A can't be B and B, A has to be A, B, in which case they commute with each other. So, it is a contradiction. So, the hypothesis that we started with, that there exist 2 elements A, B such that A, B is not equal to B, A, is wrong. In other words, G must be abelian. So, case 4 is also done. So, in case 4 we have concluded that G is abelian. So, finally, case 5. So, I want to show that in the case of order 5 group, it is abelian. So, what I will now do is the following. So, I will use the properties that the work that I have already done. So, let us say E. Okay. So, again I don't want to start with this. So, suppose G is not abelian, right. If G is not abelian, then this is exactly as in the case 4. There exist two elements A comma B in G such that A B is not B A. Okay. So, now I claim that we must have that the 5 elements, recall that G has only 5 elements, of G must be E, the identity element A, B, and B A. Why is this? Remember that A and B are elements that do not commute with each other. So, they are different from E. So, you have 3 elements here, and just as in the case 4, A B cannot be E, because if A B is E, A and B commute with each other being the inverses of each other. So, it can't be E, it can't be A, it can't be B. So, A B is a 4th element, but now in the case 4 that is done and B A must be one of them, and it has to be abelian, but now we have room for one more element. B A cannot be E, because B and A are not inverses of each other, it can't be A, it can't be B, and it is not equal to A B also, because A B and A and B do not commute. So, in other words, this is G. So, G is okay. So, this is our first observation, G must be like this. We are going to get a contradiction. So, I am going to make a series of observations. So, first, so I will claim that A B A. Okay. So, what is A B A? Remember that I want to, okay. So, maybe I will write it as a claim. A B A is B and B A B is A. So, this is my claim. So, what is the proof of this? So, and this is exactly as before. So, I am going to systematically eliminate all other possibilities. So, I will do one of them, the other being exactly similar to this. So, what is A B A? Okay, remember A B A is an element of the group. So, it must be one of E, A B or B A. So, suppose we have 5 possibilities, right. So, A B A is A, let us say. Okay. So, then just look closely at this equation. So, we can read this in 2 ways. So, we have A times B A is A and A B times A, sorry, I am considering the case E. So, I am going to consider each possibility. A B A must be an element of the group. So, it is one of these 5 elements. So, suppose it is E. So, A times B A is E, A B times A is E, right. But this is a problem now, because if A times B A is E, then B A is A inverse, and here A B is B in A inverse, right. This equation suggests that B A is A inverse, this equation suggests that A B is A inverse. But remember, when we discussed properties of groups in an earlier video, we have shown that A inverse is unique. For any element in a group, the inverse is unique, but A inverse is both B A and A B, but this means that A B is equal to B A, which is not the case, right. So, A B A can't be E. So, this cannot happen. can it be, I am claiming it is B. So, let us say can it be A? So, this is not possible, correct, is it clear? A B and B A can't be both be inverses of A. So, A B A is not E. So, that we have concluded. Can A B A be equal to A? So, I have A B A has 4 possibilities, right? E, 5 possibilities, E, A, B, A B, B A. It has no choice, it has to be one of these 5 elements. I have concluded that it can't be A. Can it be A? It can't be E. I have concluded it can't be E. Can it be A? It cannot be, because if it's A, I can cancel A and conclude that B A is E. But if B A is E, A B must also be E, because A and B are inverses of each other and they commute. So, it can't be A. Can it be A B? If it is A B, then I cancel A, then I cancel B, I get A equals E. This is also not possible. So, it can't be A B. Can it be B A? It can't be. Again I can cancel B and A and I have A equals E, right. So, it can't be B. So, A B A must be B. This is the only possibility left. So, A B A is B. This is proved. And exactly the same proof gives me B A B equals A. I have to systematically eliminate all possibilities. It can't be E, it can't be B, it can't be A B and it can't be B A. So, let me not prove that, because it is very similar to this. So, I have shown that A B A equals B, B A B equals A. Next I will claim that. So, I think I called it 1, I will claim 2, A squared equals B squared. I claim this. So, claim A squared equals B square. Why is this true? Remember, I have shown that A B A equals B. Let me multiply by B on the left. What do I get? So, I get B A equals B squared. I have also proved in the first step B A B equals A. Now, multiply by A on the left, on the right. So, I get B A equals A squared, right. So, B A equals B squared, B A equals A squared. So, A squared equals B squared. Now, the third part of the proof, I want to show that there is no room for A squared. So, let us see A squared, what is A squared? Okay, so, that is what I want to now do. A squared, if A squared, so again there are 5 possibilities, right, E A B A B B A. So, let me immediately rule out everything other than E. Suppose E A squared is A, right. This means I cancel A, one copy of A. So, that means A equals C, because A squared is A star A equals A. So, that means A equal to A E. So, that is not possible, because A is a distinct element. Can A squared be B? If A squared is B, A squared is also equal to B squared, right. So, B squared is B, because A squared is B squared and A squared is B, B squared is B. That means B is E. That is not possible. So, A squared cannot be E, B. A squared cannot be B. Can A squared be A B? If A squared is A B, I cancel A on both sides to get A equal to B, which is also not possible. A and B are distinct elements. So, A squared cannot be A B. Can A squared be B A? That would give me cancelling A, again A equal to B, which is also not possible. So, A squared cannot be A B or B A. So, A squared must be A. Okay. Now, if you recall the first part, what we have shown was, recall BAB was A. This was proved, right, in the earlier part. BAB equals A. Now, let us multiply by B on the left, no, on the right. If I multiply by B on right, I get BA is AB, right, but BA sorry, I am multiplying by B. So, BABB is AB, but what is BB? So, this gives me BAB squared is AB, but B squared is also E. If A squared is E, that is equal to B squared. So, I have shown that A squared equals B squared. So, BA squared is AB, but B squared is E. So, BA equals AB, but this is a contradiction because I have started with elements AB which do not commute with each other. So, AB and BA cannot be equal to each other. So, again we conclude that G is abelian, G being any group of order 5. Okay. So, just to recap what we have done. We wanted to show that any group of order 5 is abelian, and we have started considering order 1, which was very easy, order 2 was also very easy, order 3 was also fairly easy, order 4 was not difficult also because we easily concluded that there is not enough room. Order 5 required a little bit of work, but again we conclude that by systematically using all the properties that a group satisfies that G is abelian. So, I wanted you to focus and I wanted to do this in detail because it is a very good example. It illustrates the key points of a group, and the point that you must keep in mind and I keep emphasizing in this course is that we are studying abstract groups. Okay. These are groups, though many of the examples of groups that we know are familiar to us: integers, real numbers, rational numbers, functions, rotations, roots of unity, complex numbers. The point is these are only examples. We want to develop a theory for abstract groups. So, we cannot and we should not use any property that the specific examples have. We should only use properties that a group by definition has, namely that it has an inverse, namely that it has identity, namely that binary operation is associative, that it is closed, and those are the four important axioms. Definition, they are part of the definition, and after that you have concluded that there is a unique identity, there is a unique inverse for every element. Using these properties we are able to, and only using these properties. So, if you recall and revise what happened in this video, nowhere have we used the property that it is an integer or real number or a function. Everywhere we have only used group theoretic properties, and we have concluded that in order to achieve non-abelianness, in other words in order to produce two distinct elements that do not commute with each other, you must go up to 6 order at least, and in order 6 we do have a non-abelian group, namely S3. So, please go over this carefully and make sure that you understand everything here, and that will be a good way for you to make sure that you are comfortable with the basic definition and properties of groups. And I will stop this video now. In the next video we are going to learn about subgroups of a group and study properties of subgroups and look at various examples. Thank you.